For decades, every textbook, every scientist, every space agency told us the same story. Our celestial neighbor is a dead world, bone dry, geologically silent, a fossilized relic whose internal fires flickered out more than 3 billion years ago. The rocks Apollo astronauts brought back seem to prove it. Powdery regolith, ancient basalts, no water, no recent activity, nothing alive or changing. But something really strange is happening up there right now, and it's rewriting everything we thought we knew. In the last few years, a single nation's methodical, patient exploration program has cracked open that old consensus like a geologist's hammer on fresh basalt. China's Chang'e missions didn't just return a few more rocks, they delivered revelations that have planetary scientists scrambling to redraw the moon's biography. We've gone from the moon is arid and inert to the moon manufactures its own water, hosts exotic carbon chemistry, and was still erupting lava a billion years later than anyone predicted. These aren't minor tweaks. They're paradigm-shifting discoveries that turn the moon from a dusty museum piece into a dynamic, resource-rich world with real potential for sustained human presence. And the story of how we got here is as compelling as the findings themselves. Let's rewind. After the frenzy of the 1960s and 70s space race, humanity essentially turned its back on the moon for nearly half a century. The last sample return mission before the modern era was the Soviet Luna 24 in 1976, 170 grams of material. That's it. For 44 years, our entire model of lunar geology rested on a tiny, geographically biased collection from the near side's equatorial regions. It was like trying to understand Earth by only sampling the Sahara. We knew the data was incomplete, but without fresh samples, the models stayed frozen in the Apollo era. Enter China's lunar exploration program, launched in the early 2000s with a deliberate three-phase roadmap: orbit, land, return. It wasn't flashy showmanship, it was engineering discipline executed over 2 decades. Chang'e 1 and 2 mapped the entire surface in stunning 3D detail, spotting safe landing zones previous missions had overlooked. Chang'e 3 brought the first rover, Jade Rabbit, proving China could survive the brutal lunar night. Chang'e 4 went further, landing on the far side in Von Karman crater, deploying a relay satellite for constant communication, and even sprouting cotton seeds in a sealed mini biosphere, the first plant life to germinate off Earth. Then came the return missions that changed everything. Chang'e 5, launched in 2020, targeted Oceanus Procellarum, a vast, suspiciously young-looking lava plain on the near side. It scooped and drilled nearly 2 kilograms of material and rocketed it back to Earth, ending the 44-year sample return drought. Modern labs with 21st century instruments could finally examine lunar dirt from a brand new location. The results started pouring in almost immediately, and they were astonishing. First, the water. Not just hints of ice in polar shadows, but evidence of a dynamic water cycle operating right on the sun-baked surface. When scientists examined the lunar soil under powerful microscopes, they saw countless tiny glass beads. Perfect microscopic spheres formed when micrometeoroids slam into the regolith at cosmic speeds. The impacts flash melt silica-rich dust into molten droplets that cool mid-flight into glassy orbs. Apollo samples had these beads too, but Chinese researchers asked a new question. What happens when billions of years of solar wind slam hydrogen ions into them? The answer: the beads act like natural sponges. Solar wind protons penetrate the glass and bond with oxygen atoms inside the mineral matrix, forming hydroxyl groups and full water molecules trapped within the structure. These aren't puddles, they're chemically bound, stable even in vacuum. Crucially, the beads participate in a living cycle. Heat, saturation, or temperature swings cause them to release that water back into the lunar exosphere, where it can migrate and be retrapped elsewhere. The scale is mind-boggling. Based on the abundance of these beads in Chang'e 5 samples and their measured water content, hundreds to over 1,000 parts per million, researchers estimate the upper few meters of lunar soil across the entire moon could hold up to 270 billion tons of water. That's not locked in deep polar craters under eternal darkness. It's distributed in the dirt you could scoop up almost anywhere. For future explorers, this means heating regolith near your base could release vapor for drinking, oxygen production, or rocket fuel. The moon has been quietly manufacturing and storing its own water supply, using nothing but sunlight and micrometeorites for eons. But that was just the beginning. In 2024, another bombshell. Chinese scientists isolated a single crystal from the Chang'e 5 soil and named it ULM1, Unknown Lunar Mineral 1. Its chemical formula? NH4, MgCl3.6, H2O. Translation: a hydrated salt containing 6 full water molecules per unit, making up over 41% of its mass by weight. It also carries ammonium, delivering nitrogen, a critical element for fertilizers, life support, and even propellants that's otherwise vanishingly rare on the moon. Finding molecular water locked in a crystal lattice at mid-latitudes was revolutionary. Sunlit lunar surfaces hit temperatures that should boil away any exposed ice in moments. Yet ULM1's structure cages the water molecules like a protective vault, stable even under brutal daytime heat. Its terrestrial analog forms near volcanic fumaroles in water-rich gases, hinting at a past when the moon's interior belched volatiles that reacted and trapped these compounds before they escaped to space. This isn't just water, it's a pre-packaged survival kit of H2O and nitrogen, challenging every assumption about the moon's dryness. And then there's the carbon story, the one that really bends the mind: graphene. You know it as the wonder material of the future, single atom-thick sheets of carbon, 200 times stronger than steel, superbly conductive, the backbone of next-gen batteries and electronics. On Earth, we laboriously synthesize it in clean rooms. No one expected to find pristine few-layer graphene flakes naturally scattered in lunar dirt. Yet that's exactly what Guilin University researchers identified in Chang'e 5 samples, using Raman spectroscopy and electron microscopy. The giant impact hypothesis, the leading model for the moon's birth, says a Mars-sized body slammed into early Earth, vaporizing volatiles and leaving our satellite carbon poor. Decades of data supported this, but here was organized high-quality graphene. Not meteoritic contamination, but formed in place through an autogenous process. Volcanic gases rich in carbon oxides, combined with iron catalysts from the soil and relentless solar wind protons, apparently forged these hexagonal lattices right on the lunar surface billions of years ago. It points to a native carbon cycle we completely missed, a chemical factory quietly operating across geological time. For future settlers, harvestable carbon means local manufacturing of plastics, composites, and life support systems without shipping everything from Earth. One more gem from Chang'e 5, Chang'e Y, the first new lunar mineral discovered by Chinese scientists, a microscopic phosphate crystal containing trace helium-3 implanted by solar wind. Helium-3 is the holy grail for aneutronic fusion, clean, high-yield energy with minimal radioactive waste. The moon's regolith, unprotected by atmosphere or magnetic field, has been soaking up solar wind for billions of years, making it potentially the richest known source in the inner solar system. Even small concentrations in native minerals strengthen the case for lunar power plants, someday lighting up a permanent base. All these breakthroughs came from the near side, but the moon has two faces, and they are profoundly different. The near side is pockmarked with dark lava plains. The far side is thicker crusted highlands riddled with craters. Why the asymmetry? No one knew for sure. Chang'e 6 was designed to find out. Launched in 2024, it targeted the South Pole Aitken Basin, the solar system's largest, oldest, and deepest impact scar, likely exposing mantle material. A relay satellite, Queqiao-2, bridged the radio blackout. The lander touched down in Apollo crater, drilled and scooped, then autonomously launched its ascent vehicle for rendezvous and return. Nearly 2 kilograms of far-side material touched down in Inner Mongolia, the first ever. The biggest shock, radiometric dating of the basalts revealed volcanic eruptions 2.807 billion years ago, shockingly recent for planetary scientists. Earlier models said the moon's small size meant rapid cooling. Volcanism should have peaked 3.5 to 4 billion years ago and died by 3 billion. Chang'e 5 had already pushed near-side activity to about 2 billion years ago, explained away by localized radioactive heating from creep-rich terrain, potassium, rare earths, phosphorus. But the far side lacks that creep anomaly and has thicker crust, a heavy lid that should have stifled magma ascent even more. Yet here was clear evidence of sustained mantle melting and eruption for at least another billion years. Some fragments even date to 4.2 billion years, offering glimpses of the giant South Pole Aitken impact itself. Together, these samples are illuminating the lunar dichotomy, mantle convection, and thermal evolution in ways Apollo never could. The Moon wasn't a simple cooling sphere, it was a resilient, convecting world with a complex internal engine that defied predictions. Step back and these findings aren't isolated curiosities, they form a coherent roadmap. China and partners like Russia are building toward the International Lunar Research Station, ILRS, a permanent multinational base. The water-bearing glass beads and ULM-1 provide life support and propellant. Graphene and regolith properties enable on-site construction materials. Helium-3 hints at future energy independence. Chang'e 6 proved far-side operations are feasible. Next up, Chang'e 7, launching in the second half of 2026, will target the South Pole with an orbiter, lander, rover and hopper to map shadowed craters for water ice while scouting base sites bathed in near-constant sunlight. Chang'e 8, around 2028 to 2029, will test in-situ resource utilization. 3D printing bricks from regolith, extracting volatiles, demonstrating the technologies to live off the land. The goal, a basic ILRS outpost by the mid-2030s, expandable to orbital hubs and eventual crewed landings by 2030. This isn't science fiction anymore. The Moon is revealing itself as chemically diverse, geologically lively and resource-rich in ways the 20th century never imagined. Something really strange and incredibly promising is happening on the Moon. We're no longer just visitors to a barren rock, we're on the cusp of becoming neighbors to a world that can sustain us. The question isn't whether humanity will return to stay, it's how quickly we can build the infrastructure to unlock the treasures we now know are waiting. The next chapter of lunar exploration is already written in the rocks Chang'e brought home, and it's only just beginning.